what we want to talk about today is the path dependence of plastic strains. This is actually a very important feature of plasticity. We haven't talked about it yet. Essentially what it says is that the magnitude of the plastic strains is not just dependent on the final stress that you achieve, but it's dependent on how you got to that stress. It's dependent on the path that we took. Okay, so we want to illustrate that with an example. So just let me remind you, when we were talking about uh, uh, um, a von Mises yield function with isotropic hardening, we could write that the plastic strain increment, d epsilon ij plastic, was going to be equal to some scalar hardening function g times skl, where and then dskl, where s, of course, is the deviatoric stress tensor, times sij. Okay, so we also went on to show that for the case of a von Mises yield function with isotropic hardening, we could write g as a function that looks something like 3 over 4 times h times j2 bar, j2 bar being an internal variable that's related to the yield surface, and then h, of course, being the plastic modulus. Okay, so this is just a brief refresher um, of what we talked about previously. So we can call this equation 1, and maybe this we can call equation 2. So we want to then explore this idea of path dependence by considering the following example. So let's consider just a plain stress element in combined tension and shear loading. Okay, so consider a plain stress element in combined tension shear loading. Okay, so let's draw a little bit of a picture of this. So here's our element. Okay, so just some element that we're going to apply a stress to. We're going to apply some stress, let's say sigma 1, 1. And then we will end up with also a sigma 1, 2. Okay. And of course our directions are 1 and 2 here. So that we could write the stress tensor for this case as sigma is equal to sigma 1, 1, sigma 1, 2, sigma 1, 2, 0, 0, 0. It's plain stress, right? Something like that. Okay? What that also means is that we could write the hydrostatic component of stress as sigma m, which is equal to 1/3 of the trace. The trace is just sigma 1, 1, so it's just sigma 1, 1. That lets us also write the deviatoric stress in this case as deviatoric stress is going to be equal to the stress tensor minus the hydrostatic component. So this becomes 2/3 sigma 1, 1. This is just still stays at sigma 1, 2, 0, sigma 1, 2. This now is negative 1/3 sigma 1, 1, 0, 0, 0, and then negative 1/3 sigma 1, 1. Okay, so hopefully that's straightforward. Nothing too new. This is the stress state that we're going to look at. Okay, so we're going to go ahead and continue to assume. So we assume here von Mises yield function. Von Mises yield function with isotropic hardening. So with isotropic hardening. Okay, so that gives us kind of the rules that we're going to follow. And what we want to load is, let's just consider what we're going to load to. So let's draw a picture. We want to consider the following loading. Okay, following loading. Okay, now let's draw a picture here. Wish I could draw straighter lines for you, but apparently I can't. Okay, so this will be the sigma 1,1 axis, and this will be the sigma 1,2 axis. And if we were to plot a yield surface here, if this was sigma naught, the initial yield value, so this is 1, 2, 3, 4, 5, 6, 7, let's say, so 1, 2, 3, 4-ish, something like right in here. This would actually be sigma naught divided by the square root of 3, and we end up with some yield surface in this space that looks like this. And what we want to do is we want to load up to 2 times sigma naught in both sigma 1,1 and sigma 1,2. So this is 7, let's say 8, 9, 10, 11, 12, 13, 14 up there, and then we go up 14. I'm going to call that point, let's say. And that point is going to be 2 sigma naught, 2 sigma naught. And we're going to consider multiple ways to get there, okay? So if we consider multiple paths to get there, what we want to do is we want to say, well, one path might be here, okay? And we might call that path A. But we could also load up in this fashion. We could load up to this location, and so we could only do something like that, and we could call that path B, okay? So let me just write this out. For path A, we're going to have the sigma 1,1 for the whole time equals sigma 1,2, and both of them are going to go from 0 up to 2 sigma naught, right? And then for path B, we're going to have that actually in 2 parts. The first part, this that runs from 0 up to sigma 1,1 equals sigma naught. Well, in that case, we have that sigma 1,1, that goes from 0 up to 2 sigma naught, while sigma 1,2 is equal to 0 the entire time. And then the second part of the path holds sigma 1,1 equal to 2 sigma naught. And then sigma 2,2, it goes from 0 up to 2 sigma naught. Okay? And our goal here, what we want to look at is, so let me write this down, our goal is to compute the plastic strains, and this is the final plastic strains, right? So we want to say what happens when we get to that point for each path, okay? Okay, so hopefully you see we're going to land at the same stress point, but we're going to take a different path to get there, and we want to see what that ultimately gave us. Okay, we want to make our equations as I guess simple as possible. So I'm going to say that for simplicity, we're going to take g, that scalar hardening function, to be a constant. Okay. So remember, in the case of von Mises with isotropic hardening, we wrote that g was equal to 3 over 4h J2 bar, right, where if you remember h, we could write 1 over h was equal to 1 over E tan, the tangent modulus, minus 1 over E, okay? And you can, well, we can go ahead and then solving for, I'm not going to go through all the algebra, that's pretty basic stuff now. So let's just say solving for the E tan, okay? What we find is that E tan is equal to E divided by 4/3 J2 bar times G times E plus 1. Okay? So again, you can go back through and do all this. This is not that hard. But we know that G is constant and E is constant. So the only thing changing is potentially J2 bar. We know that J2 bar acts as that upper bound, which is going to grow with plastic strain. So this quantity is going to decrease with increasing plastic strain. And so what we get is that so as J2 bar goes up, which it will, then we can know that E tan will go down. So a constant G doesn't give you a constant tangent modulus. It actually gives you a decreasing tangent modulus with strain. So you end up with a curve that looks something, this is your stress strain curve for the material. You load up to sigma naught, and then you're gonna do something like that. Okay? So this sigma naught. This is for G equals constant. Okay, so looks really similar to the kind of curves that you're probably used to seeing. Okay, so obviously the plastic strain increments governed by this quantity SKL times DSKL. So we want to look at that for our particular case where we already wrote the deviatoric stress tensor. So let's go ahead and consider the quantity SKL DSKL. Okay, so we've already computed this before, so I'm just going to go through it quickly. This looks like 4/9 times sigma 11 d sigma 11, right? That's for the sigma 11 term, or sorry, the S11 term. Then plus it'll be a negative 1/3 squared, right? I'm just trying to remind you where these come from. Sigma 11 d sigma 11. Plus, again, the same quantity, negative 1/3 squared sigma 11 d sigma 11. And then there'll be two contributions from the stress, both the 1,2 and the 2,1. So that ends up giving us 2 times sigma 1,2 d sigma 1,2. Okay, those are our that's how we would compute this scalar quantity. We can combine these to find that this is 2/3 sigma 11 d sigma 11 plus 2 times sigma 1,2 d sigma 1,2. Okay? So that lets us write the plastic strain increment now. So now we can write d epsilon ij p. We can write that as follows. We can say d epsilon ij p is going to be equal to G, which is now constant, times the quantity 2/3 sigma 11 d sigma 11 plus 2 sigma 12 d sigma 12 times Sij. Okay? So now let's go ahead and explore. We care about two plastic strain quantities. We care about the 1,1 plastic strain and the 1,2 plastic strain. Okay, so let's go ahead and look at that. We can say that d epsilon 11 plastic strain is going to equal G times this quantity that I just wrote down times S11, which was, if you remember, 2/3 sigma 11. So we can combine these terms and end up with G times the quantity 4/9 sigma 11 squared d sigma 11 plus 4/3 sigma 11 sigma 12 d sigma 12. Okay, that's that quantity. And then we can look also at d epsilon 12 p. That's going to be G times this quantity above here. Now Sij, in the case, it's going to look like S12, which is just going to be sigma 12. And so we can then compute this, right? Write this as 2/3 sigma 11 sigma 12 times d sigma 11 plus 2 times sigma 12 squared d sigma 12. Okay, straightforward. Now let's go ahead and consider what happens here along each path. Okay, so we're going to go ahead and consider each path. Okay, so let's talk about first path A. So for path A, we said that sigma 11 was equal to sigma 12. right? Which also implies that d sigma 1, 1 is equal to d sigma 1, 2. Okay? So let me label these. We can call this equation 3 and equation 4. And let's just say we can then substitute the above here into 3 and 4, right? And we can find that then d epsilon 1, 1 p is going to be equal to, you can plug this in and do the math and find this is g times 16 ninths sigma 1, 1 squared d sigma 1, 1. And d epsilon 1, 2 p is equal to g times 8/3 times sigma 1, 1 squared d sigma 1, 1. Okay? Let's call that equation 5 and 6. Okay, so now we want to actually integrate equations 5 and 6 so that we can integrate from from whenever we cross that yield surface up to d sigma 1, 1 equals 2 times sigma naught. But we need a lower bound of integration. Okay, so we want to integrate equations 5 and 6. So equations 5 and 6, but we need a lower bound of integration. Okay? Why do we need that? Well, obviously we can start out, we're starting out at sigma 1, 1 equals 0, but we know that plastic strain doesn't accumulate until we hit that yield surface. So we need to know along that trajectory, the sigma 1, 1 equals sigma 1, 2 trajectory, we need to know where that crosses the yield surface. So let's look at that. So remember we had our yield function, which was J2 minus J2 bar, and we said that initially that first yield surface is 1/3 sigma naught squared, and then we can also go ahead and compute J2 for our problem. So for J2 for this problem, if you go back, remember that's 1/2 Sij Sij. For this problem now, that's going to end up looking like 1/3 sigma 1, 1 squared plus sigma 1, 2 squared. In the case when sigma 1, 1 is equal to sigma 1, 2, then we have that J2 is going to be equal to 4/3 sigma 1, 1 squared. And we can go ahead and find out then that equating 4/3 sigma 1, 1 squared to 1/3 sigma naught squared, we can find that sigma 1, 1 is going to be equal to start out at 1/2 times sigma naught. Okay? So this is our lower bound of integration. Okay? So let's go ahead and do that. So integrating, here's equation 5. We want to say here's epsilon 1, 1 plastic going to be equal to the integral of d epsilon 1, 1 plastic, right? Which we can say is the integral from, now we know the lower bound, 1/2 sigma naught up to 2 sigma naught times the quantity, integrating the quantity 16 ninths sigma 1, 1 squared times d sigma 1, 1. In this case, obviously g is constant, 16 ninths is constant, and so we can write this integral as 16 divided by 27 times sigma 1, 1 cubed, evaluated from 1/2 sigma naught up to 2 sigma naught, which you can go ahead and do the algebra from there, but it ends up coming back to 14/3 times g times sigma naught cubed. Okay? Let's integrate then sigma 1, 2. Right? Going to be integral over d epsilon 1, 2 plastic. Similarly, it limits, because we wrote everything in terms of sigma 1, 1, 2 sigma naught When we do this integral, this is integrating now g times 8/3 times sigma 1, 1 squared d sigma 1, 1. And when we do the integration there, you can carry out the integration and find this comes out to be 7 times g times sigma naught cubed. Okay? So these are the two numbers that we're going to take into account, and we're going to compare with what we get from the other path. So these are the plastic strains that accumulated during that load path from 0 up to sigma 1, 1 equals sigma 1, 2 equals 2 sigma naught. Okay? So now we want to consider load path B, right? Now load path B, remember, had two stages. Stage 1, which said sigma 1, 2 equals 0 into stage, and then sigma 1, 1 went from 0 up to 2 sigma naught. So let's go ahead and now substitute that into our equation for the plastic strain increment. D epsilon 1, 1 P then from our previous equation gives us G times 4/9 sigma 1, 1 squared d sigma 1, 1 plus 4/3 sigma 1, 1 sigma 1, 2 d sigma 1, 2, right? And sigma 1, 2, and actually d sigma 1, 2 for this stage is 0. So we're left with the quantity g times 4/9 sigma 1, 1 squared d sigma 1, 1. And then if you remember d epsilon 1, 2, we had that as g times 2/3 sigma 1, 2 sigma 1, 1 d sigma 1, 1 plus 2 sigma 1, 2 squared d sigma 1, 2, right? Sigma 1, 2 is 0. This whole thing then is 0. So no plastic strain accumulates in the 1, 2 component. So we can just now integrate this first equation. So integrate d epsilon 1, 1 P to get the plastic strain during substep 1. So this is going to say epsilon 1, 1 P is going to be equal to, obviously, the integral d epsilon 1, 1 P, which will be equal to, what's our limits here? Well, we know that along the sigma 1, 1 axis, it begins at sigma naught, and we go up to 2 times sigma naught. So this one is pretty straightforward. So here we have g again times 4/9 sigma 1, 1 squared d sigma 1, 1. Okay, you can go through, carry this out, and find that this equals 28/27 times g times sigma naught cubed. So I want to remind you, this is for part 1, right, of the path. Okay, now we have to examine part 2. Okay, in part 2, we had that sigma 1, 1 is going to be fixed at 2 sigma naught, and then we also had that sigma 1, 2, right, is going to go from 0 up to 2 sigma naught here. Okay, so let's go ahead and write down what the strain increment terms are. So d epsilon 1, 1 P, remember that's going to be equal to g times 4/9 sigma 1, 1 squared d sigma 1, 1 plus 4/3 sigma 1, 1 sigma 1, 2 d sigma 1, 2. Okay, well, how much is sigma 1, 1 changing? D sigma 1, 1 for this entire thing is 0. So even though sigma 1, 1 is positive, d sigma 1 was 0, so this term goes away. And we're left with 4/3 times g times sigma 1, 1, which is fixed, right? So this is fixed at 2 sigma naught times sigma 1, 2 d sigma 1, 2, which gives us 8/3 g times sigma 1, 2 d sigma 1, 2. Okay? Let's do the same thing for d epsilon 1, 2 plastic. Okay, we have g times the quantity 2/3 sigma 1, 1 sigma 1, 2 d sigma 1, 1 plus 2 times sigma 1, 2 squared d sigma 1, 2. Same argument, d sigma 1, 1 for this is 0, so that goes to 0. And we're left with 2g times sigma 1, 2 squared times d sigma 1, 2. Okay? So now we need to integrate these. Now, so let's talk about epsilon 1, 1 p. It's not so simple to say we're just going to integrate d epsilon 1, 1 p exactly, because we now have a non-zero term here. This term was that 28 27ths g times sigma naught cubed up to there. So we actually end up with, we write that as 28 27ths g times sigma naught cubed. That's what we had originally. Then plus, we can now write this with our stress term, going from, the stress goes from 0 up to 2 sigma naught, and this quantity is 8/3 g times sigma 1, 2 d sigma 1, 2. And you can carry this out. I'm not going to go through it all just in the interest of time. This becomes 272 divided by 27 times g times sigma naught cubed. Okay? So that is a quantity we're going to use for comparison. And then we can also compute epsilon 1, 2 plastic. It doesn't have anything to start with, so we can just directly integrate that. So epsilon 1, 2 plastic, that's going to be equal to the integral from 0 to 2 sigma naught of 2 times g times sigma 1, 2 squared d sigma 1, 2, which you can readily find is just 16/3 times g times sigma naught cubed. Also a quantity we want to compare. So let me just summarize here. So here's a summary of what we just computed. We said that for path A and then path B, okay, and then we were interested in, and I'm going to write this as epsilon 1, 1 plastic divided by this constant g sigma naught cubed, right? And for path A, we ended up with something that was approximately 4.7. This is approximately 10.1. And if we looked at 1, 2 plastic, again normalized by sigma naught cubed, we have this quantity that, sorry, this is not an approximate, you can go back and show this is identically 7, and this is approximately 5.3. Okay? So if you want to divide those out, you can. Okay? So what's the upshot of this? The highlight, okay, and this is important, the highlight is that the loading path affects the plastic strain that's accumulated. What does that mean? That means that I can't just look at where I am in stress space and tell you how much plastic strain there was. I have to know how it got there. It's important that the history is critical here. Okay, so this is just, again, hopefully a basic example, one where we kind of could solve it closed form to get to demonstrate that there is this load path dependence.